Okay, welcome to Chapter 13, Particle Force and Acceleration, dealing with Newton's Law. So, what you've seen many times in other courses and a little bit here already. Newton's Law, the sum of all external forces is equal to mass times the acceleration of the particle. So mass of the particle times acceleration of the particle. Now we are just going to extend this slightly to note that when you have multiple particles, you can write this equation as the following. The mass of the individual particles times the acceleration of the individual particles. And of course these are all vectors, so we'll just add these in here. And we will note that if you were to find the center of mass of these various particles, this would also equal the total mass times the acceleration at the center of gravity relative to these particles. All right. So that's where we're heading for this chapter. That's the basic equation. It's time to start looking at the problems. And another page. All right. So here's the first one we're going to take a look at. Here we go. So here's our first problem. So what I have here are two motors, A and B, and there's winding drums associated with each of these motors. So they're pulling rope off here, pulling rope off there. They're going at separate rates. This one's accelerating at 2 feet per second squared. This is 3. And so if we look at these pulleys, this distance is fixed, that distance is fixed, that distance is fixed, distance around the pulleys is all fixed. The variation here is how much rope does this one pull off, how much does that pull off, and then we'll just create a distance. This is pulley C, so I'll set a reference up right here, and we'll measure down to that spot. We'll call that DC. So we have DB running off this way and some amount of rope DA running off that way. So from our work that we've done with pulleys already, we know we can write DA plus DB plus 2DC equals some constant, which I'll just call K. Take the derivative twice, and we would have AB plus AA plus AB equals minus 2AC. So these are A positive this direction, B this direction, C measured down. So as these pull off this way, this is going to go up, which relative to this coordinate system is negative, so that's making sense for us. All right. So we know A, we know B, so that would be 2 plus 3 divided by 2, so AC for the current situation is going to be minus 5 over 2 feet per second squared. All right. So we know, and that's relative to this coordinate system. Now the question for this problem is find the acceleration of C. Well, we've done that relative to this coordinate system, and find the tension in the rope. So that's the next part we're going to do. So for this thing, I'll use more of a conventional coordinate system. Set up X and Y in the usual way. And let's solve this here. Now, if we were to put this on an exam, this is a fairly simplistic problem. We could have elements that are the same. I've seen this many times. People they form this free body diagram. They'll just say, oh, 2t minus 300, t is 150. No. This thing is accelerating relative to what we have here, up at 2.5 feet per second squared. If it's not accelerating, yes, then t is 150. But it is accelerating up, so you have to account for that. And so that's simply some forces in the y, which would be, we have 2t's going up minus 300 going down, is mass. Then we have to convert mass, or weight, 300 pounds into mass, so 300 divided by 32.2. And now we put in our 2.5 up. Solve for t. We get 161.6 pounds. All right. So this takes us to our next problem we're going to look at. And so this is sort of a James Bond problem. So picture there's a real bad guy up here. And he'll put a little gun in his hand, sort of thing. All right. So bad guy up here. And so James Bond is going to kind of releases the rope. There's some big mass sitting here, and so that'll pull him up, and he'll be climbing up the rope as it goes. So, given the rope, block attached to one end, Bond on the other side, and what we're given is that he is accelerating currently at 0.25 meters per second squared due to climbing. Block is 80 kilograms. I have Bond here at 150 kilograms. All right. So we're asked to find the tension in the rope, acceleration of the block, acceleration of the person. Okay, so we have free body diagrams here. We'll just put a B for the block there. All right, so let's just look at the block. We know its mass, and it's just hanging there. So we can sum forces, which I'll actually bring up here. If we sum the forces in the y, we have T minus 80 times 9.81 equals mass, which is 80, times the acceleration of the block, which I'll call AB. So there's equation 1. Now the person, which I've drawn as a block, because once you draw this, you just can't beat it. All right? So here we have T minus 75 times 9.81. So here we're summing forces again. Mass, well, we know that. But when we go to put acceleration in, we have to think about this. So here's the deal. This, what we're told, is human acceleration relative to the rope. Well, what's the rope doing? Rope's going up. What rate's it going up at? From an acceleration point of view, whatever this one's going, hopefully down at. Otherwise, Bond is fighting it. So this is hopefully accelerating down at some rate, and then he's climbing up relative to that. Whatever rate this is going down at, on this side it's going up at that rate. So I'll put in AP here, but what I'll note is that, and if I look here, I have 1, 2, 3 unknowns. But what is AP? AP is simply minus AB plus how fast he's going relative to the rope. Then there we go. We now have 1, 2, 3 equations, 3 unknowns. And so all we need to do then is solve that. And so if this were me, I would solve this one for t, solve that one for t, and stick this into there and solve for AB. You go through this process, you will come up with AB is minus 0.195 meters per second squared. So that is indeed going down. AP is 0.445 meters per second squared. So that's going up. Tension will work out to 770 newtons. I'll leave you to do the 3 equations and 3 unknowns, and we'll be back shortly with more video.